I hope everyone can see my screen.
Yeah, full screen, please.
Yeah, okay.
Thanks.
Good afternoon, everyone. However, I'm not connected from Switzerland. Now I'm in Canada, so it's morning already. Yeah, first of all, thanks all the committee member for organizing this virtual workshop and inviting me. I'm talking about application of fault scarp dating using colorine 36 to track activity of normal fault in Western Anatolia beyond the existing earthquake records. For sure, everyone here is familiar with this figure, so I'm not going into the detail. Everyone knows that how Turkey is active and aware about the Samos disaster. So I just go to the main issue, like everywhere in the world, that the main issue is always the lack of data and the time span that all these historical and instrumental earthquakes are recorded are not really long enough to enable us to assess how often destructive earthquake happens and to determine the amount of displacement and also to approximate the timing of future ones. So with this knowledge that the area is already active, we did fault scarp dating in Western Anatolia with the aims of determining the age of past earthquakes, the amount of vertical displacement, the magnitude that was responsible for these ruptures, recurrence interval, and approximate timing of future ones. So this is simplified geological map of Western Anatolia, which is geomorphologically characterized by east-west trending grabens, which consist large-scale normal faults, which are locally built in limestone. And this makes this area an ideal place to apply fault scarp dating using colorine 36. What we did is we selected seven key normal faults in 3 Ingedis Graben. We have Rahmiye here, Mugir Tepe, and Monastir. And along the Büyükmenderes Graben in its western part, we have Kalafat, Yavansu, and Priene-Sazli. And along the Gukova Graben, we sampled Oren fault. We did sampling for fault scarp dating of these faults. I just proceed to our method. Actually, our method is based on reaction of cosmic rays with the normal fault surface. Just imagine in this figure that we have a fault here. It's exposed here, what's covered by collovium in the lower section. We show concentration of colorine on this axis against the position on the fault scarp here. So you'd see that for the exposed part of the fault, we have a constant amount of colorine 36 production, but below the surface, because of the shielding effect of collovium, the production is decreased towards the depths. In this animation, I just show you how the colorine 36 concentration pattern looks like when we have 4 similar earthquakes of similar size. Again, imagine we have a fault here. It didn't rupture yet. It's totally covered by collovium. So at T1, we have the first rupture and with the slip amount of S1, and the ground level moves from G0 to G1. So for the concentration of colorine, we have such a convex form. Just compare with this figure. So this convex form shows the time that the fault surface was already covered by collovium. And the time passes, we have the second rupture at T2. Again, we have a slip of 2 and the time of inactivity, but this sharp discontinuity between these two convex forms represent the timing of earthquake. And then we have at 3T and 3-4, finally the last earthquakes, and the ground level, I mean the collovium level finally reached to the current ground level that is here. So if we built up all this concentration, we have such a pattern for the colorine 36 concentration, and this is what we model in fault scarp dating using colorine 36. what we did in the field. Actually, I'm not going into the detail for all of these field, the faults, but I just show you all the figures from the field work, but mostly focus on the results from Calafat and Yavansu. For sure, they are not directly related to Samos earthquake, the fault responsible for the Samos earthquake, but they are kind of aligned with that. So I decided just mostly focus on this faults. So first we go to Gedizgraben to show you Rahmiye, Mugirtepe, and Monastir faults. This is our this is the Rahmiye fault from the far distance. This is our sampling site, and in a closer view we have this. It's a really flat and nice fault surface. So we have some Roman excavation here, and we just did sampling right here. That looks like this. First, what we do is we mark all the samples on the fault scarp like this. It has dimension of 10 and 15 centimeters, and then the profile should be continuous from the ground level upwards the fault surface. So we collected 87 samples here. And also what is important to be measured is geometry of the fault. The scarp deep, top surface deep, collobium deep, scarp height, and also another important thing is to determine the exact top and bottom position of each sample. This is Monastir fault scarp. We had three profiles. Sometimes because of this kind of patches and high amount of erosion, shifting for a few meters is allowed for this method. And then the geometry of the fault is shown here. And the Mugirtepe fault just close to Monastir. And then we move to western part of Büyükmenderesgraben. We have Calafat fault and Yavansu here, and Priene-Sazli here. Sampling site is here. Actually, Calafat and Yavansu fault are considered as the displays of long Kushadase fault zone, which are kind of aligned to the fault that is responsible for Samos earthquake. So these two are located on the opposite side of a hill, Calafat mountain. We go to the field. This is the trace of Calafat mountain here. And the closer view, you see that the fault surface is almost vertical. So normally to have access to the upper side of the fault, we use a scaffold. And you see the 54 samples is collected here, and geometry of the fault is shown. Move to the other side of the hill and go for sampling for Yavansu. 68 samples are collected here. And you see, again, because of these patches, we just shift a little bit to the left for the upper side of the fault. And another important thing is that determining the reference point. Reference point is defined as the collovium level just after the final earthquake model. So we just define this by looking at the surface and difference of freshness between the exposed part of the fault and already covered part of the fault by collovium. So here, the reference point is determined to be here. So we had like 4 to 5 samples just below the ground. More to the south, Priene-Sazli fault. This is the fault trace. Sampling site here. 4 profile are installed here for collecting samples. And a closer view, 117 samples are collected, and geometry of the fault is here. And along the Gokova Graben, the Oren fault has been sampled. This is our longest and highest surface. The fault and surface collected is already 12 meters long. You can see from here how high the fault surface is, and about 130 samples are collected here, and it already has a record of a recent disaster at 2017 and geometry of the fault. And our lab work, I don't go through all the lab procedure here, but I just briefly say that we almost treated like about 600 samples for AMS and the other elemental analysis. And these are our results from Calafat and Yavansu without any simulation. Again, we have concentration of colorine here against position along the fault scarp. So each of these points represent a concentration of colorine in individual samples along with their uncertainty. And you see that we have like 4 samples below the ground collected. And how we model. We use a MATLAB code using written by my colleague Dmitry Tikhomirov. Name is fault scarp dating tool. First, we build our database based on all the input parameters like geometry of the faults and all the AMS and other elemental analysis. And then we run the code for modeling based on different scenarios in terms of the number of earthquake, the age of earthquake, and also the amount of displacement that occurred during these ruptures. And finally, the most realistic result will be selected based on the less difference between the measured and theoretical ones. So for the Calafat fault, we could model 3 earthquakes, about 15.3, 8.4, and 3.6 thousand years ago, with the slip amount of about 1 to 3 meters. So this is the oldest one, and then the youngest one we have here. And the slip rate has been calculated. And for the Yavansu fault also, we have 3 earthquakes recovered, about 8 kilo years ago, 3.4 and 2. And with this amount of displacement, and slip rates are here. Here I just summarize the time slip history of these 2 faults. We have Calafat Mountain. Calafat fault is in the north, and Yavansu we have here. The earthquake model for Yavansu are here, and Calafat are shown here. So we see that the Calafat fault first had a rupture, and then when it had the second rupture, almost at the same time, Yavansu got ruptured too, and the youngest ones are also more fitted. You see the age is 3.4 and 3.6, and finally we had a rupture in Yavansu fault. So to control the plausibility of modeling, we used empirical relationship, and regardless of modeling actually first, and then to see how big earthquake we can expect if these faults are activated and how much displacement that they can produce, and then compare with our modeled displacement, and found out that these earthquakes, especially these younger ones with a larger amount of displacement, they are consist of like clustered earthquake. The earthquake that just occurred close in time, that unfortunately the code is not able to detect them as individual earthquake. I'm not going to show you, because lack of the time, not show you all the results from the other faults, but I just compiled all the output here. You see the ages for the earthquake are here, and they are nicely correlated somehow. And for example, Pre-Nasazi and Oren fault show recurrence interval. Their recurrence interval are regular and show like 2,000 years of difference. And then slip rates are in general increasing through the time. And the earthquake responsible for this rupture were mainly in average 6.5. In this graph, I just plotted all the ages along with the uncertainty. So at least 20 major seismic activity over the last 16 years has been recovered, which most of them occurred as clustered earthquakes of magnitude in average 6.5. If we consider the age correlation, we can somehow say that every 2000 years, we can introduce like 4 activity phases, and which almost simultaneously all of these faults were activated. And in addition to our time with the frequent record of frequent earthquake, we can say every 1000 years we have a really high seismic activity. And some of them are perfectly correlated with the historical records we have here in Monastir, and the other one on Pirin Sazli. The historical records are these ones. Now I just zoom out a bit more from the Western Anatolia to a regional scale of Aegean Sea, and to take a look at the other normal faults in this region, in Italy, Greece, Turkey, and Israel. And what was interesting was that in general, this recurrence interval is kind of common between the normal faults of almost similar size in this region. Now we can connect the deformation pattern of Western Anatolia with the faults that we studied. Actually, everyone knows that African plate is being subducted beneath the Aegean plate, and because of this, on the African plate, we have formation of strike slip and lots of thrust faults as a result of shortening. But in Aegean, above the Aegean plate, and especially Western Anatolia, due to back arc extension procedure, lots of normal faults are formed. So, and the exact amount of this, this convergence is not clear yet, but the number between 10 to 40 millimeter per year has been estimated. So these large movements just transmit a large amount of stress on the faults in Aegean plate, and especially Western Anatolia, and especially on the faults which are parallel and subparallel to the convergence trend. And more stress will be loaded on the larger faults. And part of this energy is consumed as seismically consumed. So that's why we have a frequent and a large amount of earthquake on this side. So, and anyway, we cannot stop this earthquake from happening, but with every polar earthquake study we do, we can just take a step forward for better seismic risk assessment, and also to help to minimize the value of damages. And the slip rate that we calculated is up to 2.4 millimeter per year for the faults, which in general increasing through the time. So it can kind of indicate that the faults in Western Anatolia are not mature. I mean, they are still propagating and they're tightly interacting with one another, and their stress field is tightly influenced on each other. And also, it can tell us that our time with records of very large earthquakes and frequent earthquakes can be considered as the most active period during the Holocene time. To sum up, we recovered at least 20 major seismic activity, mostly as clustered earthquakes. We introduced 4 phases of high seismic activity with at about 2, 4, 6, and 8,000 years ago, and with the recurrence interval of almost 2,000 years, which fits somehow to a series of normal faults in Aegean plate. And most of the faults are seismogenic, and actually all of them. And the slip rate acceleration shows that our time is the most active period through the entire Holocene, and the faults of Western Anatolia are still propagating and growing. And what about the next high seismically active period? With this finding, it's not far beyond expectation that we have the next one in 2000 years. Thank you so much for attending. And if there is any question.